So hopefully the structure, how we went about implementing this design is reasonably clear. Let's look at how we would test this. So the test bench is also a slightly complicated beast out here, right? We have a few parameters, right? Extensive use of parameters throughout this. We use a parameter for the clock period. We also put in a test timeout parameter, which is interesting. It's something that we'll look at a little bit later. It's useful in test benches to catch a scenario where maybe your logic got stuck and is not behaving the way that you expect, right? You could change these numbers. I have given the same values. I've written shorthand for simulation, but you have these are actually the same values that are present in the test bench. You can play around with these numbers and try to shorten them, or you might have longer values in the actual test cases, but shorten them for the case of the test bench. It doesn't matter, and in this case the numbers are small enough that the simulation anyway goes through very quickly. I'm also adding a couple of counters over here. This is purely for the test cases, right, which just counts the total number of tests and also how many of them failed. There are a few intermediate values, right? I don't need to worry about declaring them as reg or wire over here. That's why logic exists in SystemVerilog. But if it was Verilog, then these would probably all be declared, well, most of them would be declared as reg, right, except for the ones that are coming as output. So for example, lights underscore ns is coming as an output of the traffic controller, so it would need to be a wire, right. So SystemVerilog makes that a bit easier, right, but keep in mind that the simple, if you are dealing with Verilog, anything that you need to set as part of this test bench inside an initial block or inside an always block is a reg. Anything that is coming from your DUT, for example, right, and needs to get updated as something that came out of the DUT, almost certainly needs to be declared as a wire. Okay, what I am doing is I am defining all the parameters out here, right, but I am also being a little bit lazy and just using this DUT.star in order to do the named instantiation, right. So I am actually sort of saying, hey, whatever is defined as clock over here connected to the clock of my DUT, whatever is defined as reset underscore n over here connected to the reset n of my DUT, and so on. This is usually fine. The reason I say that you have to be careful, as I mentioned in an earlier lecture, is in case at some point you modify your DUT and add an extra signal to it and you do not have an equivalent signal out here, things can go wrong, right. It may not map the way that you expect it to. So to avoid that, it's usually safer and cleaner to make this explicit, but as long as you follow good conventions, this is reasonably safe to do as well. Okay, clock generation, we already looked at how clock generation can be done for sequential circuits. We just do forever hash clock period by 2 clock equal to tilde clock. We start off with clock equal to 0, which means that we'll start off with a portion of 0, and then at clock period by 2 is when we have the first passage of the clock, which is fine. You could choose to make clock equal to 1 as your starting point so that your passages are aligned with multiples of clock period directly. Now comes the actual test stimulus, right. We set up our counters, right, and then we initialize the signals. First things first, reset n equal to 0, it's an active low reset, so this is actually pulling the entire system into reset, and the two inputs pedns and pedEW, we set them both to 0. This is just a starting scenario, right. Now what I do is I basically I tell it to wait for a certain amount of time. Now this is one way of doing it. Hash clock period into 2 basically means wait for 2 clock periods, right, and then set reset n equal to 1. But then you will see that on line 58 there is this line saying wait cycles of 1. Now what is wait cycles of 1? It doesn't seem to be a regular Verilog piece of code. So I'm just going to jump ahead a little bit, and when we go down we will see that there is a helper task, right, that's defined on line 145, and it's a task that basically takes an integer as input and does a repeat for whatever is this input number of cycles at passage clock. In other words, it waits for that many positive edges of the clock, which is a extremely nice and useful way to use a task in Verilog, right. It basically allows you to just write a small piece of code like this. wait cycles of 1, right? And that's enough to basically say, okay, now wait for 1 clock cycle. I can also say wait cycles of 10 and it will wait for 10 clock cycles. I can say wait cycles of, well, ns green time in this case, which is, well, the green time has basically been defined in terms of number of clock cycles, right? So by saying wait cycles of ns green time, I am just going to wait for that many clock cycles before proceeding beyond this point. As you can see, a potentially nice use case for a task. Okay, so now what do my test cases look like? The first one basically displays what the test is about, right? It basically says test case 1 basic cycle without pedestrians. And the first thing that we need to do is check that the lights ns has the value 001, that is it's green, and lights EW is in 100, that is it is red. Now what is check lights, right? Once again, it does not exist, it is not part of Verilog. It means that it is a task that we have defined. Let us go down and see how it is defined. This is a more complicated task, right? It basically says that it has multiple inputs out here. There is a string that it takes as input, right? So a task can actually take a string as input. A module can also take a string as input, but that's most likely not synthesizable if that's the case. In this case, this task is not meant to be synthesized, it's meant to be part of my test bench. So that's good, right? I can use a string inside it. It also takes the logic which basically says what the actual ns and actual EW values are versus the expected ns and expected EW values, right? And if the things are not equal, it basically prints an error, right? And if necessary, you can make it just stop right now and say that, you know, it failed, right? And just basically print an error and immediately exit the simulation at this point. Over here, I don't want it to exit immediately because I would like to see if there are other test cases that it might pass. What I do instead is I increment the failed count, and I also increment the total count over here irrespective of whether it passed or failed the test, right? So that is my task. In other words, every time that I call check lights, it can be considered as one test case. Okay, let's go back and look at this. So test case 1 basically checks the ns green state, whether the lights ns and lights EW have the value 001 and 100. These are the actuals, light ns and lights EW. These are the expected, right? 001 and 100. Okay, now after that is done, I basically wait for ns green time. What do I expect after ns green time? It should have timed out of the green state and gone into the yellow state. So automatically I should be switching to the yellow, to the east-west green. But for that, I actually need to wait some more time. I need to wait for yellow time plus red time. I have waited only for the amount of green time over here. I need to wait for the yellow time plus red time. And after that, if I check, I should find that the north-south is on red, east-west is on green. So test case 1 and test case 2 are both checking the normal regular functionality of the system. Now test case 3 basically says I want to look for the ns green and then I want to give a pedestrian request. Now this is a really nice way of doing it. I can just basically wait for state ns green, right? So rather than sort of trying to reset the system and so on, I know that eventually it will time out and get back into the ns green state. How do I check for that? Yet another task, right? Task wait for state ns green while the lights ns is not equal to green, just let the clock pass. Similarly, I can wait for state EW green, wait until yellow, wait until yellow east-west. So yellow north-south or yellow east-west, right? By checking the appropriate signal out here. Alright, so go back over here and I have this test case 3 which says wait for the ns to become green, wait for a few clock cycles, 10 clock cycles. I have given hash of clock period into 10, I could also have given wait cycles of 10, both are exactly the same. Well, one goes based on passage clock events, one goes just based on the amount of time, but they achieve the same result. After 10 clock cycles, this is arbitrary, right? I just chose to wait for 10 clock cycles, make pedEW equal to 1, keep it 1 for 2 clock cycles and then make it equal to 0. What should happen after that? If I wait a little bit of time, I should find that the ns became yellow. Okay. Now, why did I need this wait cycles of 3? This is because the FSM actually takes some cycles to synchronize the input signal. We already saw that when we were discussing the actual implementation. If I did not have that synchronization delay, I should be able to check immediately in the next clock, and it should have gone to yellow. Okay. But let's say we wait for 3 clock cycles and then we find that it should have become transition to yellow. Alright, now I am going to write another test case which is multiple pedestrian requests. Okay, if this passed, then I don't really care what else happens out here. I just wait for the EW green state. Again, easy, I just put a wait for EW green, right? And this essentially is some very impatient person who is just pressing the same button 5 times, right? They press the button, release it, press it, release it 5 times. Okay. What should happen over here is that after waiting for a certain amount of time, I should be able to check the lights and say that it has actually gone into the east-west yellow. Okay. Now what we should be able to do is I should be able to wait for a certain amount of time, right? And as long as I am not waiting for a very long time, I should find that I am still in the yellow state, because what has happened over here is I gave 1, the FSM actually responds to the very first pedNS request. The further sort of repeated pressing of the button doesn't really make any difference to it, which means that by the time I get to this check lights, I should already find that I am in the yellow state, because it's going to be in yellow for nearly 500 cycles, right? And you might see this commented out line over here. You can sort of play around with it by changing how many cycles you are going to wait and see whether it actually transitions as expected or not. Okay. And well, one more test case we have added, which is just let the system run for a little while, activate the reset, wait for 2 clock cycles, remove the reset, wait for a little while and check that it should be in the NS state. Okay. So well, it actually doesn't matter the fact that you were in yellow to start with. As soon as I reset it over here, when I come out of reset, I should be able to check the lights as I have. One last thing, there is also in the test bench something called a watchdog timer. This is not a hardware watchdog timer, this is a test bench watchdog timer. Basically what it says is it's an initial block. All that this block does is waits for this amount of time, hash of clock period into test timeout. In this case, test timeout was set to something like 100,000. So it waits for something like 100,000 clock cycles and then prints an error and finishes. So this looks very strange, right? I mean, what exactly is this piece of code doing? It looks as though it's always going to print an error and then finish the simulation. The point is, if my test bench actually worked properly, I would have gone through all of these test cases, displayed this number of tests completed successfully and finished before this condition ever got satisfied, right? So my simulation would finish right here without ever allowing this timeout to happen. But for some reason, let's say that one of these things, one of these check lights or one of these wait for the condition that we had, which was, let's say, wait for state NS green, let's say that that got stuck in a loop and NS green never happened. What would happen is that after a certain amount of time, my watchdog timer would kick in and say simulation timeout, possible deadlock, and would stop your simulation for you anyway, because you know that there is no way that the system should be running for 100,000 clock cycles. Okay, that's a lot of talking. Let's see what happens when I actually try to run this simulation, right? And the way that we can run this is I am using the iVerilog compiler. The compiler for this basically says iVerilog, I need to give the traffic control test bench first, and then the traffic control .SV. You will notice that both of these are SystemVerilog, because of which I also need to give an additional flag to iVerilog, which is basically telling it to use the 2012 version of Verilog, which basically includes SystemVerilog, right? And what I can do is I can say -o traffic tb. It doesn't matter if you don't, by default it will create a file called a.out, right? But I can give this traffic tb. In this particular case, the version of iVerilog that I am using is a slightly older version, right, which complains about task definitions, not having an empty port declaration list and so on, right. This is more of a sort of what's called a linting error. It's basically a warning. It's not a syntax error. It has gone ahead and created your simulation executable for you, and you can run the simulation. How do I run the simulation? I would type in VVP, which is the Verilog processor, right, and the name of the file that I just created, traffic_tb, okay, and it's pretty much instantaneous. That's why, you know, I spent all the time going over the code, because actually running it is very fast and a bit of an anticlimax because it just finishes instantaneously. But test case 1, test case 2, all of them went through without any errors, and it finally says 5 of 5 tests completed successfully. Okay. Now, hopefully, right, we have actually written the code properly and we have written the tests properly, but you need to have that confidence that your test cases are actually testing the right thing, right. An example of that is, let me go in there into my test bench, and you know, so for example, one of these things I could say that, let's look at the, this test case 3, right. You remember I told you that I need to wait for 3 clock cycles before the signal has turned to yellow, right. So the NS going to yellow after the pedestrian, I need to wait for 3 clock cycles for the synchronization to happen. What if I did not? What if I only waited for 1 clock cycle, right? Let's take a look at what happens there. I will once again compile my Verilog, and I will once again run the code, and now you see that there is a problem here. It actually says incorrect lights, NS is still in green, right, whereas I expected yellow, and that's because I have not had enough time over here to actually synchronize and then go into the yellow state. Okay, so that sort of gives me a little bit more confidence that maybe my test bench is actually doing the right thing and it's not just, you know, letting everything pass. Now, one more thing I wanted to demonstrate, which is that, okay, now this looks good that everything passed, maybe my implementation was great. Is there a possibility that it would actually have helped me catch a bug? So I created an example with a bug in it, okay. And the bug, if you go through and look carefully, in this case I am just going to explain the code, you know, what the bug is, but it's also always a good exercise to, you know, try and modify the code a little bit, try and see what kind of bugs it is generating, right. In this case, what I am doing is, the bug essentially is right on this piece of code that we see over here, right. If you look carefully, you will realize that on line 102, when I am in state NS green, I just check if I time out, I need to go into the yellow state. The original was, as we can see down here in the EW green, right, I should have checked either for timer done or for the ped, in that case EW pressed, right. So that part has been removed over here, right. So you can see that in the original traffic signal, it had that, it had this timer done or ped EW pressed, whereas in the buggy code, I have left that part out and I am only checking for timer done. Do I have a test case that will catch that? Well, yes, it turns out that my pedestrian request during NS green hopefully should catch that problem, okay. So let's go in here and say I will do this iVerilog compilation, but now the only thing I am changing is I am changing the file that I compile, right, to the one which contains the bug, and yes, it compiles, and what happens when I run it? Now you can see that it once again generates an error on test case 3, right. It basically says that it was 001. Why? Because what I did in this case was, in my test bench for test case 3, after having applied this, I wait for 3 clock cycles, which I know is enough for synchronization, and then move into the check for whether it has moved to yellow. Now, if I did not actually respond to ped EW, I should remain in green because I am waiting for a timeout which is like 1000 clock cycles, right, which definitely has not happened within the time that I have given over here, right. And sure enough, what we see is that it actually fails that condition and says that that particular test failed. The other tests continue to pass, and therefore it ends up saying that 4 out of 5 completed successfully. This is a good way, as I said, of having self-checking test benches. Okay. So to summarize, basically what we have is, you know, state machines are a very important part of how we implement control logic in large systems, and how we code them, there are usually a lot of different conventions in terms of how we write the code, right, which allows us to implement them efficiently. There are certain things which come into play such as timing as well as synthesis and optimization and so on, which we'll understand more about when we actually get to details on the implementation of the synthesis parts of the logic. But having a good test bench and more importantly thinking of all the different ways in which a system can fail and encoding them as test cases is very important. This particular test bench is a very simple test bench. It is not testing a number of different things that should ideally be added. And given the fact that the test cases actually run pretty fast, there's absolutely nothing stopping you from adding tens of test cases over here. Just to make sure, for example, over here we only tested what happens when there is a NS walk signal while NS is green, right, or the pedestrian walk signal while NS is green. We should test what happens when there is something when EW is green. We should check whether the priorities are handled properly. We should have timing checks which make sure that the red and yellow and so on are also handled for an appropriate amount of time. So there are many other test conditions that can be added on that can actually be used in order to check that your overall implementation works properly, right. And one interesting approach from the software world about how to go about even building software or building systems like this is to first define your tests and then see, okay, how do I make the tests pass, right. This is sometimes referred to as test driven development. The important point about it is that, you know, having a clear notion of when your system is actually working and whether it's working properly is crucial to sort of being able to have a properly tested piece of hardware. All of this is simulation. Once you have got it working in simulation comes the next part of it, which is actually checking whether it synthesizes properly and then behaves correctly after synthesis, right. But if it fails in simulation, you know that you have pretty much failed step 1 and you know you need to fix that before you move forward at all.